drawing here. And so this is another great example, much more practical example of homeostasis. So we've got this car in the image here. And so we start off with our car kind of trying to ascend this hill. It's going at about 60 miles per hour. And as we start to ascend the hill, and as we get to the foot of the hill, we see that the weight is slowing down, right? The weight that this car is traveling is now going about 55 miles per hour. Now, when we've dialed in our set point, so our set point is pretty much where we want, not where, but how fast we want this car to be going. And so we dial in our set point at about 60 miles per hour. And so when we start to ascend the hill, the foot of the hill, and the speed of the car reduces because, gravity and because we're trying to ascend the hill, that is going to send off what we call an error signal. Because we've established that we want to keep the car going at 60 miles per hour, when the speed now reduces to 55 miles per hour, that's going to be cause for concern. That's going to be cause for alarm. That's going to set off what we call an error signal. Now, as we continue to ascend the hill, something has to happen to get us back to 60 miles per hour. And so that correction is, in this scenario, increasing the amount of gas that's flowing to our engine. As we increase the gas flow to our engine, we're going to see that the car can now speed up once again. And so we get to 58 miles per hour and then eventually back to 60 miles per hour. And so what this example really underscores is that we've got a set point variable that we would like to maintain. We've got an error signal, and an error signal is an alarm or a signal that's sent whenever we deviate from that set point. Now, this example is showing that the deviation happens to be a decrease, but we can also think about a deviation being an increase. Let's say we were going above 60 miles per hour. That would also initiate an error signal. The next thing that happens is some type of corrective measure in order to help us to get back to our set point. And what we'll see is that as the corrective measure takes place, in this example, it happens to be speeding up the car, sending more gas to the engine to help with that speeding up. As we do that, as we institute this corrective measure, the error signal gets smaller and smaller and smaller. When we get back to our set point, the error signal is turned off altogether. Okay, and so these are the players, these are the variables, these are the different mechanisms and components that are important in bringing about and maintaining homeostasis. And so we can use this example of a car and translate that to our physiology. We can use a whole host of different examples: blood pressure, blood volume, pH, and we can think about those variables in the exact same way as we're thinking about speed here, is that anytime we slightly deviate from our set point, we then have an error signal. And the purpose of the error signal is to alert the system that some change, some corrective measure needs to be instituted in order to get us back to that set point. And as that corrective change is instituted, that error signal becomes smaller and smaller until it's diminished and turned off altogether, okay? And so we can look at some of the components here. The regulated variable, that is the aspect that we wish to maintain. In our example here, it's the speed. But in our physiology, we want to think about things like blood pressure, which I mentioned before, things like heart rate, things like body temperature, things like our plasma volume, right? Those are some of the regulated variables in our physiology. We can also describe the set point as another component of homeostasis. And that's going to be the expected value of said regulated variable. Again, the example in this, or the set point in this example, happens to be the speed that we want our car to be maintained at, and that happens to be 60 miles per hour. If we translate that to our physiology, our set points are things like blood pressure. Usually, we like blood pressure to be about 120/80. We like pH to be about 3.45. And so those are some set points of our physiology. And so the set points are where we expect those variables to be. And once again, if we deviate from those values, we then start to initiate some error signals, okay? Let's talk about some other terms that are important for understanding homeostasis. There's negative feedback. Now, negative feedback is the mechanism that corrects that initial change. If we have a regulated variable decrease, our system was going to initiate changes in order to increase that variable in order to bring it back to set point. We can also have that in the opposite direction. If our regulated variable increases, the negative feedback mechanism is going to decrease that variable to bring it right back to set point. And so this is going to be that self-correcting measure. So without me even detecting it cognitively, if my blood pressure raises, my body's going to be trying to do everything it can to get it to decrease, to get it back to set point. And the opposite is true as well. And then the fourth important term here is going to be the error signal. That is essentially the difference between our set point and then the regulated variable at that time. And so essentially it's the difference between where we want to be and where we currently are. And so there's that degree. We can have a large error signal. If my blood pressure is really high, that degree of that error signal is going to be proportional to the degree with which I am, away from that set point. And the opposite is going to be true as well. So it's essentially how far we are from the set point or the value that we would like that regulated variable to be at. Okay.
So the way I'm understanding it, the negative, what was it called again? The negative feedback. Negative feedback. It makes the negative feedback makes our body re-regulate and make sure we keep in homeostasis.
Excellent. Yes. So that's a good way of phrasing it. So it's going to kind of keep regulating things, but it also needs to be detecting small changes. And as it detects those small changes, it simply moves that variable in the opposite direction in order to be a self-correcting change.
Okay, that makes sense.
Okay, great. We'll talk about another part of this, which is positive feedback. It's not as relevant for homeostasis, but it's going to be changes happening in the opposite direction. We'll talk about that as well. But negative feedback is the most important mechanism for maintaining homeostasis. It's essentially detecting small changes and then making the opposite change in order to get us back to that set point. And we'll talk about some more examples as we go along. So in this example, we're using blood glucose levels as our regulated variable. And then we want to think about the terms that we described for homeostasis and think about how they relate to this example. So here we're talking about our blood glucose, essentially how much glucose is floating around in our plasma. And if we think about the terms that we mentioned before, what can you describe the set point as in this example? What is our set point in terms of blood glucose?
100.
Excellent, 100. That's where we like blood glucose to be. That's where the body strives to keep our blood plasma glucose. And so 100 is going to be our set point. Now, in this example, let's say we just had a really large, starchy or carby meal. And so we've got a lot of glucose circulating in our blood. What does that initiate? What do we call that initial raise or spike in the blood glucose?
An error signal.
Excellent. So that's going to be our error signal. Remember, anytime we deviate from where we like to be, that is going to institute an error signal. And the degree of that error signal is going to be proportional to the degree with which we are away from that set point. Okay. And then some type of change is going to happen in our physiology to help correct this deviation from set point. In this blood glucose example, it's going to be glucose moving into our cells and out of our blood so that we can clear the blood of excess glucose, but then actually start absorbing that into our cells to be used or to be stored. And so that's going to help to lower that blood glucose back down to normal. And so we're going to call that the decreasing of the error signal as glucose is absorbed into our cells and used for energy. We then see that glucose leaving the blood. And so we decrease our plasma glucose, we decrease our error signal, and we get back down to our normal blood glucose. Okay. And so we're looking at this example in terms of a deviation that increases our variable away from set point, but also think about someone who may be diabetic or who may be, who may have gone without food for a while or fasting. And so when we see that blood glucose drop, below 100, we also want to be thinking about the corrective changes that would be happening to bring that blood glucose back to normal, if possible, right? So we think about things like glucose being made in other parts of the body, glucose being released from storage in our kidneys and muscle and liver. And so glucose being moved from our tissues into the blood in order to raise that blood glucose and try to get it back to 100. So I want us to be thinking about these changes from both ends of the spectrum, either a deviation that increases and then the negative feedback, which would decrease that variable, or a deviation that decreases and a negative feedback that would increase that variable. The whole goal here is to keep us at that 100 milligrams per deciliter, which is our set point. Okay. Last few minutes here, let's talk about the components to homeostasis. So these are basically structures, physical structures in our body that are a part of the loop, which we call instituting homeostasis, if that makes sense. So we've got receptors, we've got integrating centers, we've got effectors, we've got signals, essentially the players of homeostasis. And so as we look at this example here in this schematic, we can think about these players in different parts of this homeostasis loop. So let's talk about an example of you standing up really quickly. Let's say you were lying in a supine position and you stood up really quickly. Your blood pressure is going to drastically fall as most of the blood in your body, because of gravity, kind of pools down into your legs, okay? Now, when you stand up really quickly, that initial change is going to be detected as a stimulus by a receptor, okay? And so essentially the receptors are going to be the first parts of our system that pick up those changes. That's going to send a signal to our that's going to send a signal to our integrating centers, which are up in the brain. So think about the medulla oblongata or the pons even. And these centers in the brain are pretty much going to analyze the situation, analyze the signals that are being sent from that stimulus and determine what change needs to happen in order to correct that, signal that's coming from that stimulus, okay? Then from the integrating centers, we then have the effectors, and the effectors are, what are the organs, what are the structures, what are the body systems that are actually going to bring about the corrective change? In our example here with blood pressure, if I stand up really quickly, and then my blood pressure falls, the receptors are going to detect that change in blood pressure. They're going to send some signals up to my medulla oblongata. And then the corrective change would be to increase my heart rate so that I can appreciate a raise in that blood pressure. And so the effector is the organ that actually helps to bring about that change. So when we speed up the heart rate because of the signals that are sent from the brain to the heart, increasing the weight and the contractility of the heart, making our blood pressure, raising the blood pressure essentially, that is eventually going to correct that initial signal, and that's going to turn off the error signal, which was that drop in blood pressure. Okay, and so here we really see an example of translating the players, which we are looking at here with the components or the terms that we talked about before, and then seeing how that plays into the loop, which brings about homeostasis.